Welcome to the deep dive. Today we are strapping ourselves into the command chair of the Modern Security Operations Center, or the SOC,
Mhm.
because frankly, the current environment is becoming, well, unsustainable for human analysts.
It really is.
We're just seeing this perpetual tsunami of alerts and log data coming from all these complex multi-cloud environments. The sheer volume,
Yeah,
it just outpaces any human team.
it absolutely does. And that volume, it isn't just noise or signal in there, but we can't process it fast enough.
Right.
We've hit this critical inflection point where you can no longer just staff your way out of the problem. You can't just throw more people at it.
No.
We need machine speed detection, machine speed analysis, and response. So our mission today is really to move past that old concept of reactive firefighting
Okay.
and dive deep into what we're calling the Microsoft Sentinel Watchtower, a centralized, high-altitude view that automates defense and really empowers the human analyst.
Okay, a watchtower. I like that analogy. Let's unpack this shift in the paradigm. Our sources lay out a pretty clear foundation built on a key technology triad that makes all this automation possible.
Right.
We're talking about Microsoft Sentinel, which is the platform itself.
Mm-hmm.
Then KQL, the Custo query language, which is like the analytical engine for the proactive threat hunting.
The agent.
And finally, Azure Logic Apps, which provide the powerful SOAR capabilities. That's security orchestration, automation, and response. That kind of closes the loop.
The synergy between those three, it's not just a collection of tools. It's the complete architectural blueprint you need to transform a security practice from reactive and, completely overwhelmed
Yeah.
to automated, proactive, and truly AI ready. So if you, the listener, are tasked with modernizing your CCOPs, this deep dive is going to give you that exact foundational knowledge and even some specific detection logic you can use.
All right, let's start with the architecture itself. Because before we can even talk about automation, we have to understand where the visibility is coming from.
Of course.
And it seems like the first thing we have to clarify, and probably the most confusing point for a lot of people, is the difference between Microsoft Defender and Microsoft Sentinel.
Yes.
They're in the same ecosystem, but they have very distinct roles.
They do, and they're complementary. I think the best way to think about this is in terms of altitude.
Okay.
Microsoft Defender XDR, that's extended detection and response, it operates at ground level. We call it the firefighter on the ground.
The firefighter.
Defender's core focus is real-time detection, prevention, and response, right at the individual workload level. So we're talking about protecting specific resources, your VMs, your containers, databases, endpoints, cloud identities, email.
So if some zero-day malware lands on a corporate laptop or a VM, Defender is the system that steps in and actively intercepts the execution.
Yeah.
It isolates that machine or blocks the malicious connection right there at the source before the payload can even do its thing.
It's focused on high-fidelity, immediate tactical action. Now, Sentinel, by contrast, is the Watchtower spotting threats from above.
Right.
It functions as the cloud-native SIEM security information and event management and the TOL platform. Sentinel doesn't really care about a single machine.
It's looking at the whole picture.
The whole picture. It aggregates, correlates, and analyzes security data across your entire digital estate. And critically, that includes multi-cloud and multi-platform environments, not just Azure, but AWS, GCP, your identity providers, your SaaS apps, everything.
So the real strategic value then is Sentinel stitching together the complete attack narrative.
Yes.
An individual alert from Defender might just look like one suspicious file execution, but Sentinel takes that, correlates it with a failed sign-in from your Entra ID logs, sees a huge spike in proxy traffic from a firewall, and it uses that holistic multi-stage view to uncover a complex attack pattern that no single tool could ever see on its own.
That holistic view is absolutely non-negotiable for handling modern attacks. And the foundational efficiency of Sentinel is built on its ability to handle data ingestion at a massive scale.
What kind of scale are we talking about?
We're talking about connecting to over 350 native data connectors right out of the box. These pull data seamlessly from all the Microsoft sources, Entra ID, Azure Activity, Office 365, Defender signals. But they also integrate logs from nearly every major third-party security solution using standards like syslog or CEF.
Okay, but hold on. That's where the complexity should logically start, right, Paul?
How so?
If you're pulling in logs from hundreds of different sources, different firewalls, different cloud providers, the log formats must be an absolute linguistic nightmare for any analyst trying to write a single query.
And that is the primary pain point that Sentinel's data normalization solves. This is where the Advanced Security Information Model, or ASIM, comes into play. ASIM provides that crucial standardized schema layer. I mean, imagine trying to manage 350 different vendor log schemas, where each one calls a source IP something different. Source IP, source address, client IP. It's paralyzing.
So SM just fixes that by saying, look, we don't care what the vendor calls it. From now on, we're calling it a P address.
Precisely. ASIM translates all those diverse logs into a uniform single view. That standardization is what lets an analyst write one KQL query that works consistently across different vendors. It abstracts all that complexity away.
It sounds like magic, but what's the practical overhead? I mean, is writing the necessary ASIM parsers for custom logs a huge resource drain? Does it slow down adoption?
It can be, initially.
Yeah.
And let's be fair, writing custom ASIM parsers, that requires dedicated detection engineering time. It's a classic trade-off.
Mhm.
You spend time upfront building the parser correctly to get high-quality, normalized data.
To save hundreds of hours later.
Exactly. To save hundreds of hours later, when analysts are hunting and writing rules, if you skimp on ASIM adoption, you basically sabotage your own future hunting efforts by locking all your data into silos. So yeah, it's an investment, not just a switch you flip.
That makes sense. Okay, so let's break down the whole SOC toolkit that operates within this normalized Watchtower. Beyond the core SIM functions, what are the other specialized components?
Right, so we have 5 key components that have to work in concert. First is the core SIEM functionality, which we said is that centralized log consolidation and forensics engine, all driven by KQL.
Got it.
Second is the SOAR capability. Powered by Azure Logic Apps, it handles the rapid machine speed orchestration, automation, and remediation. That's the action engine.
And then we get into the intelligence layers that provide all the context.
Correct. That's components 3 and 4. UEBA, User and Entity Behavioral Analytics. It uses machine learning to create behavioral profiles. It doesn't just look for known bad things. It builds a baseline of what's normal for a developer, what's normal for HR, and then it flags statistically anomalous behavior.
So if an IT admin who usually logs in from Chicago suddenly starts querying financial databases from a new region, UEBA flags that behavior, not the credential itself.
Exactly. It spots the deviation from the peer baseline. Component 4 is Threat Intelligence, or TI. This contextualizes your internal signals with external threat feeds. So if a suspicious IP shows up in your firewall logs, the TI component instantly checks if that IP is linked to a known nation-state actor or a malware C2 server.
Which dramatically improves the fidelity of the incident.
It does. And finally, that 5th massive component is the data lake. This provides long-term, cost-effective storage for historical hunting and compliance. It can retain high-volume, low-fidelity data for up to 12 years.
So integrating all these pieces, SIEM, SOAR, UEBA, TI, and the data lake, it's not just about collecting features. It's about achieving real, quantifiable goals for the SOC team.
Absolutely. The main measurable objective is the reduction of mean time to detect MTTD and mean time to respond MTTR. By using analytics, UEBA and TI, to group hundreds of noisy, low-fidelity alerts, say 500 failed logins, into just one coherent high-fidelity incident, Sentinel dramatically reduces alert fatigue.
Right.
Analysts spend way less time sifting through noise and way more time on actual high-value outcomes. The Watchtower just minimizes the distractions so the analyst can focus on the real fire.
That is a phenomenal setup for the platform. So now we can move into the actual analysis, the proactive defense part, which means diving into KQL, the Kusto query language. This is truly the language that powers the Watchtower. What exactly is KQL, and why has it become the primary engine for this kind of deep proactive hunting?
Well, KQL is the engine because it was purpose-built for massive volumes of time series data. It's a read-only request language optimized to process petabytes of data and return tabular results with incredible efficiency. Its unique strength is its syntax. You start with a data table, and then you use pipe-separated operators. That vertical bar to filter, transform, and aggregate data in a sequence of steps. It's like a pipeline for security intelligence.
So for the security analyst who's transitioning into this world, what are the absolute foundational concepts they need to get about KQL to be effective right away?
It starts simply, but you have to be precise. Every query must begin with the table name, like signin logs or device process events. That name is followed by the pipe robe, which feeds the table into the first operator.
Okay.
The next most fundamental operator is where. It's used to filter rows based on conditions. You'd almost always use it to filter by the time-generated column, maybe with the OGO function, to limit your search to a relevant window, like the last 48 hours.
And you mentioned an operator that's critical not just for clarity and speed, but maybe even for cost management in a service like this.
That is the project operator, and I cannot overstate how critical it is.
Why?
When you run a query across billions of rows, you only want to retrieve the columns you actually need: the username, the IP, the time. Using project limits the output to only those specific columns. If you forget to use project, you're pulling back massive amounts of unnecessary data, which slows down your query and, yes, in some cases, contributes to higher data processing costs.
So if I forget project and I pull 50 columns when I only needed 3, the difference is measured in dollars and processing time, not just seconds.
Absolutely. It's a core tenet of KQL performance tuning. It's an efficiency imperative.
Okay, let's get practical then. Let's look at the most common attack surface.
Yeah.
Identity compromise, specifically logins. We hear 2 terms all the time: brute force and password spraying. Can you clarify that distinction and how KQL differentiates them?
This is a crucial distinction for detection engineering. A brute force attack is high-volume password attempts against a single account. They just hammer one account over and over.
Right.
A password spraying attack reverses that. The attacker tries 1 or 2 common passwords like Winter 2024 across many different accounts.
The spray. It's designed to fly under the radar of those traditional account lockout policies.
Precisely. It distributes the attack load, so it's much harder for a standard system to flag it as suspicious. Therefore, our KQL logic has to focus on the source IP's activity, not the target account.
So how do we actually write the KQL to catch that kind of systematic campaign? Walk me through the steps.
Okay, so we need to look for correlation. We query the SIGINT logs table, filtering immediately for error results, specifically result type equals 50053 or 50126, which are your invalid username or password errors.
Okay.
Next, we use the summarize operator, combined with a crucial aggregation function, the count.
The distinct count function. Ah, that's what isolates the uniqueness of the targets.
Yes. The full logic would look something like summarized total attempts count, unique accounts target, decount user principal name by iPad address bin, time generated 1 IT.
So the decount user principal name tells us how many unique users were targeted by that one IP in that hour.
Exactly. Then you apply your thresholds. If we find an IP that tried to log into, say, more than 10 unique accounts and had more than 30 total attempts in that hour, that's a high-fidelity incident. That's a spraying campaign.
And that immediately lets the security team stop worrying about 30 individual users and start focusing on blocking the bad actor's IP address. That's speed.
That is the power of aggregation in KQL. And speaking of aggregation and source location, KQL is also excellent for geographic anomaly hunting.
How specific can you get with that?
Very specific. You can use KQL to filter out all your known trusted locations. Then you can spot a login attempt from a high-risk region or just a country you have no business in. One source shared a story of an analyst caching a failed login from Argentina when the real user only ever worked from the office in Bangalore. Now, sometimes it's just a misconfigured VPN, but it's an event that warrants immediate investigation.
That's turning an anomaly into real intelligence. You also mentioned the spooky hunt, detecting failed sign-ins from disabled accounts.
Yes, the spooky one. Why would a disabled account suddenly show up in the logs?
Right.
It often means there are old, forgotten scripts trying to run with those dead credentials. A simple hunt like SIGINT logs, where identity contains disabled surfaces, these ghost attempts. It's basically a prompt for some necessary spring cleaning to get rid of latent attack surfaces.
Let's pivot from identity to execution, specifically living off the LAN, or LOTLO techniques, where attackers use legitimate tools like PowerShell to hide.
LOTL is so prevalent because these binaries are trusted by the OS. So KQL has to target the suspicious arguments or command line parameters used with them. A classic example is hunting for encoded PowerShell execution. That's an immediate sign of obfuscation.
What are the signatures for that?
You'd query logs like device process events from Defender for endpoint, looking for command lines containing NA or the string base64. Another powerful detection is finding the stealth flags used to hide the execution window.
The silent, hidden execution that just runs in the background.
Exactly. This is pure defense evasion. The query logic specifically looks for flags like no profile and window style hidden. We heard an anecdote from an analyst who ran this exact query. They weren't even looking for malware.
What did they find?
They found a quiet backup script running every midnight that was pulling sensitive documents from a company folder and dumping them onto someone's personal OneDrive account.
Whoa. So the hunt caught a massive corporate data policy violation, not a cyber criminal.
It did. The software was legitimate, but the purpose was unauthorized data egress. It just highlights the dual value of proactive hunting. You find security threats and compliance gaps.
Okay, moving to more advanced scenarios.
Yeah.
Data exfiltration. Cloud storage accounts, Azure Storage, SharePoint, OneDrive. These are the crown jewels. How does KQL help protect against things like storage ransomware?
You have to start with the prerequisite, visibility. For Azure Storage, you absolutely must enable diagnostic logs. We call it the holy trinity of logging: storage read, storage write, and storage delete. Without enabling these logs, you're flying blind.
So once those logs are flowing, what's the behavioral pattern we look for that defines storage ransomware?
The primary pattern is the smash and grab. It's a rapid sequence of mass write and mass delete activity. Ransomware encrypts a file in place, that's a write operation, and then it deletes the original unencrypted file, a delete operation.
That dual action, high volume activity in a tight window is the signature.
Can you walk us through the specific KQL logic for that?
Sure. A high-fidelity detection involves querying storage file logs for operations like put range or delete file. The key is temporal correlation. You use summarize to count the number of writes and deletes by user and IP, grouped into a very short time window, maybe DIN, time generated, 15 meter.
Okay.
If you find a single entity generating, say, more than 50 writes and more than 50 deletes in that 15-minute window, it's highly indicative of ransomware. That's basically hunting on a budget using KQL to build a sophisticated behavioral alarm system.
That's the essence of detection engineering. And beyond ransomware, we look for anomalies in access methods to catch quieter data theft. One very effective technique is hunting for unusual user agents.
Why the user agent?
Because most legitimate employees access files through standard interfaces: Windows Explorer, a mobile app, a web browser. These use common, benign user agents. Attackers, however, often use raw tools designed for bulk data access to bypass those interfaces.
So we're hunting for the technical strings that signal automation, not a human clicking around.
Exactly. We look for tools like rclone, AirCopy, or generic scripting identifiers like Python or lib. Finding any of those strings in the user agent header field of your storage logs is a massive red flag for exfiltration. It tells the SOC that a raw, non-standard tool is touching your data.
And finally, let's talk about the data hoarder scenario, the volume-based detection in Office 365.
This is a simple but essential behavioral hunt. We look for an abnormally large data egress volume from a single user. If an HR employee who normally downloads 10 megs a week suddenly downloads 10 gigs of payroll data, that's a shift that demands investigation. You track the Office activity table for the file downloaded count. Identifying a single user downloading, say, more than 500 unique files in 1 hour from SharePoint is a clear, volume-based indicator of mass data egress.
That wraps up a really comprehensive view of KQL. We've established it gives us the power to see these complex threats, but seeing the attack, even 15 minutes after it starts, doesn't stop the damage.
Right.
That leads us directly to the speed of response, which is where SOAR comes in.
That is the perfect transition. Detection without a rapid, consistent response is just insufficient today. SOAR, security orchestration, automation, and response, is the framework that guarantees that machine speed response. In Sentinel, this is powered by Azure Logic Apps workflows, which we just call playbooks.
Let's clarify those terms, because automation and orchestration get used interchangeably, but our sources say they're fundamentally different.
They are distinct building blocks. Automation is simple. It's programming an individual, discrete task to run on its own, like automatically blocking an IP address.
Okay.
Orchestration is the higher level capability. It's about connecting multiple different tools, firewalls, ticketing systems, identity providers, so they can act as a coordinated group across the whole environment. Orchestration is what enables enterprise-wide automation.
And the playbook, built on Logic Apps, is the mechanism that defines the steps for both.
Yes. Playbooks are just collections of remediation and enrichment actions. They have a dual trigger mechanism, which is critical. They can be triggered automatically by an automation rule in response to an incident, or they can be triggered manually by an analyst during a hunt.
What are the most common high-value use cases for these playbooks?
The sources highlight 4 essential categories. First, enrichment collecting extra data, like running a WHOIS lookup on an IP and attaching that context to the incident. Second, bidirectional sync, automatically opening and closing tickets in systems like ServiceNow.
And the response mechanisms.
Third is orchestration for communication, sending automated alerts to the SOC's Teams or Slack channel. And fourth, the most critical, response and containment. Immediate actions like isolating a machine, forcing an MFA re-registration, or blocking a user.
Let's focus on containment. Can you walk us through a complex, real-world example? Let's say stopping a high-risk, compromised user with a multifaceted playbook.
Okay, this scenario is for high-fidelity incidents, like that confirmed password spray we talked about. The goal is rapid containment while mitigating the risk of a false positive.
So walk us through the step-by-step logic.
The flow begins when a Sentinel incident is created. An automation rule immediately calls the playbook. Step 1 is notification and enrichment. The playbook opens a ServiceNow ticket and sends an initial alert to the team's channel. Step 2 is where we inject caution.
Right, because immediate blocking could cause business disruption if it's a false positive, especially for a critical user. So how do you inject human control into a machine speed process?
This is the human control logic layer. The playbook sends an interactive email to a designated senior security admin. That email has two clear buttons: block user and IP and ignore incident. The workflow then pauses, waiting for a human response.
Okay, so once that human approval is given, the block button is pressed, what happens next?
If the admin selects block, the playbook immediately executes parallel containment actions. It sends a command via the Microsoft Graph API to Entra ID to disable the user. At the same time, it connects to the firewall to block the originating malicious IP at the network perimeter.
And if the admin determines it's a false positive and hits ignore?
Then the playbook follows an audit trail cleanup branch. It closes the incident in Sentinel and closes the corresponding ticket in ServiceNow, ensuring the bidirectional sync is complete and the audit trail is clean.
That's robust. Let's get really specific on the mechanics of blocking a user in Entra ID. That sounds like an incredibly privileged action.
It is. The Logic app communicates with the identity system using an HTTP action. Specifically, it executes a passCH method directed at the Microsoft Graph API endpoint for that user.
And the body of the request.
It's minimal but highly effective. Account enabled. False. That single line immediately disables the account.
And what if the incident had, say, 15 compromised accounts?
The Logic app handles that automatically using a loop. It just iterates through all the affected user accounts that are extracted as entities from the incident and runs that passCH request for each one.
But automation needs to be transparent, especially when it fails. How does the playbook report back what happened?
Transparency is handled through parallel branching and array management in that loop. If the HTTP request succeeds, the account name is appended to a success array. If it fails, maybe due to a permissions error, it moves down a failure branch. There, a parse.json action extracts the specific error message from the HTTP failure body, and that detailed error is appended to an error array.
So you're capturing precise reason why something failed, not just that it failed.
Exactly. And the final step is summarizing it for the analyst. The last action is add comment to incident, v3 in Sentinel. This comment uses if and join expressions to cleanly display the results. Something like action, user block, successes, John, Jane, failures, Bob, permission denied.
That's incredibly detailed. But let's go back to security. This automation connects to the Graph API, which is arguably the most privileged surface in the whole environment. Who manages the security of the Logic app itself? What permissions are needed?
That is a critical point. The Logic app needs its own identity. When an automation rule triggers the playbook, the Microsoft Sentinel service account needs explicit permissions. Specifically, the Microsoft Sentinel automation contributor role on the resource group where that playbook lives.
And that's just to let the automation rule run the playbook.
Right. It's a necessary evil for incident-triggered responses. For an analyst who might manually trigger it, they need the less privileged Microsoft Sentinel Playbook operator role. The risk is managed by scoping these roles using the principle of least privilege.
We've established the architecture and the core tools, KQL for hunting, Logic Apps for response. Now let's move to the most strategic element, artificial intelligence. How is AI being integrated to scale this Watchtower capability?
The integration of generative AI tools, mainly Microsoft Security Copilot, is designed to address the sheer cognitive scale of incident triage and analysis. It's not a replacement, but an intelligent copilot embedded right in the workflow.
So it's not just speeding up response, it's radically augmenting the analyst's speed of comprehension.
Precisely. The productivity gains are transformative. Our sources show triage times are up to 78% faster, leading to teams saving over 200 hours per month.
Wow. How does it do that?
Two critical ways. First, instant summarization. It summarizes an incident by answering the who, what, and where immediately, consolidating data from the maybe hundreds of individual alerts attached to that incident.
Saving the analyst from reading every single log entry.
Yes. Second, and this is maybe the most democratizing part, it translates natural language requests into executable KQL code. An analyst can describe the hunt they want to perform in plain English like, find all failed logins from outside the US last week that used a generic user agent, and the Copilot just generates the complex KQL query automatically.
That's fascinating. It lowers the barrier to entry for deep analysis, letting analysts focus on the security hypothesis, not the syntax. You also mentioned a specialized agent for the health of the Watchtower itself.
Yes, the Watchtower Health Agent. Sentinel is useless if the data stops flowing. This agent performs continuous proactive health assessments. It's constantly monitoring for things like sudden significant changes in log volume, what we call variance analysis.
Why is variance analysis so important?
Because a massive drop in firewall logs might not be a failure. It could be an attacker trying to suppress logging to hide their activity. The agent flags this deviation. It also identifies disconnected data sources and provides optimization recommendations, like suggesting you remove low-value rules that are just driving up ingestion costs.
Let's talk about data retention, which ties back to that data lake component. For serious forensics, you need to look back way longer than 90 days. How does Sentinel manage huge volumes of historical data without making every query cripplingly slow or expensive?
That's handled by the data lake tier, which decouples storage from compute. This tier is for long-term retention, up to 12 years of high-volume, low-fidelity logs like DNS records or firewall flow logs. Storing them here is significantly cheaper than in the faster analytics tier.
But if an analyst needs to query data that's years old, are they forced to run these slow interactive queries that could time out?
Not necessarily. They have two modes for KQL on the data lake. First are interactive queries. These are good for quick spot checks, but they're limited. They might time out after 8 minutes or return only 500,000 rows.
Okay.
Second, and far more powerful, are KQL jobs.
What's a KQL job?
It's an asynchronous query. It can be a one-time or scheduled query capable of processing massive data sets over the full 12-year window. You submit the job, and it reports back when it's done.
What's a real-world scenario where you'd absolutely need a KQL job?
A prime example is retrospective analysis after a zero-day disclosure. Let's say a threat intel report identifies a C2 node that was active 6 months ago. An analyst can submit a KQL job to search all historical firewall logs in the data lake for any interaction with that IP.
I see.
Detection engineers also use them to build time series baselines or uncover subtle credential abuse patterns that only show up when you look across many months.
And if they find something actionable in those old logs?
They use a process called data promotion. If a KQL job finds relevant logs from, say, 18 months ago, those specific logs can be promoted back into the faster analytics tier. This makes that historical data immediately available for correlation with current incidents, letting the analyst build a complete long-term attack timeline.
This whole structure suggests that building a world-class defense isn't just about installing software. It's a systematic, engineering-driven approach. Let's close this section with the crucial detection engineering lifecycle.
That lifecycle is the non-negotiable standard for modern SecOps. It guarantees continuous improvement and ensures your technical efforts are aligned with the evolving threat landscape. It's a disciplined, 6-step cycle.
Walk us through the steps.
Okay, let's use the example of a newly discovered technique. Step 1 is intelligence gathering. The engineer monitors threat feeds to identify this new tactic, technique, and procedure, or TTP.
So you know what the adversary is doing now.
All right. Step 2, KQL development. The engineer writes a precise KQL query to capture that TTP while minimizing false positives.
Then comes baselining, which feels essential for determining fidelity.
Step 3, baselining. It's vital. You run that new query against 30 to 90 days of historical data to understand the normal volume of results. If the rule generates 500 alerts a day during the test, it's too noisy. You go back and refine the query. This prevents thousands of false alarms on day 1.
Once it's baselined and validated, the hunting query becomes an alert.
Step 4, analytic rule creation. Convert that query into a scheduled alert rule in Sentinel. Define its severity. Map the critical entities. Step 5 is automation and SOAR. This is where you attach the playbooks for enrichment and rapid containment, maybe with that human approval layer we discussed.
And finally, the long-term health check that closes the loop.
Step 6, continuous monitoring. You use tools like the Watchtower Health Agent to ensure the rule stays functional as your environment changes. If a log source gets disconnected or the query stops working, you get an alert.
And every step along the way should be mapped to the MITRE ATT and CK framework, which provides that strategic overview.
Absolutely.
Yeah.
MITRE ATT and CK mapping gives you the visual coverage map. It lets leaders see high-level gaps. If you have great detection for initial access, but nothing for exfiltration, you know exactly where to prioritize your next development effort.
We've covered massive ground today, moving from the philosophical problem of alert overload all the way to the granular mechanics of automated threat response.
Yeah.
The modern AI-ready SOC is really defined by these three pillars working in synergy.
That's right. Sentinel provides the centralized multi-cloud visibility, the SIEM XDR. KQL provides the analytical power for proactive threat hunting, letting you detect everything from password sprays to behavioral ransomware. And Azure Logic Apps provides the agile SOAR engine for rapid, audited containment and orchestration. This synergy fundamentally empowers the human analyst by automating the mundane and neutralizing threats at machine speed.
The era of manual triage is rapidly fading away. The goal isn't just surviving the daily alert volume anymore, it's leveraging engineering and automation to leapfrog the attacker's speed entirely. The most efficient SOC is one where the analysts spend less time looking at alerts and significantly more time perfecting the automation that prevents those alerts from ever escalating in the first place.
Indeed. And it forces us to ask some tough questions about that trade-off between trust and speed. We've seen how powerful those automated playbooks can be.
So here is the final provocative thought for you to chew on. If you were responsible for protecting the crown jewels, knowing you had a confirmed high-fidelity signal of a compromised entity, what is the single most critical, highly sensitive action you would decide to automate fully without requiring any human approval?
Ooh.
Would it be isolating a compromised machine, disabling a known malicious service account, or maybe automatically deleting a malicious email from every single inbox? Think about that razor's edge of trade-off between speed and risk.
Great food for thought that closes the loop on where the future of SecOps really sits. Thank you for joining us for this deep dive into automating the cloud watchtower.
We'll catch you next time.